All right, here we go. This is essentially Unit 1, so let's get started. So here's a basic chemistry review. Now I know that you guys, whether you are 9th grade or 10th grade, have taken physical science, either in 8th grade or 9th grade. So this stuff should be a review. The words covalent, element, proton, neutron, electron, atom, and molecule, all right? So a substance that cannot be broken down into another smaller substance we know is an element. The smallest possible unit of said element you know is an atom, right? Positively charged particles in the nucleus of an atom, they start with a P, positive P proton, okay? Neutrally charged particles, so they don't have a charge, neutral neutron. Negatively charged particles, this is the one that's left over, they fly around the outside of the protons and neutrons, okay? And you'll learn a lot more about them in chemistry class. Electrons, and a bond formed when two atoms share electrons. Sharing electrons is covalent, and two or more atoms linked together by sharing electrons is the last one, and that would be a molecule. Now, so all of these things help define water. So we need to understand some background knowledge, remember some background knowledge, so that we can understand the properties of water, because water, as far as we know, is the basis of life. And what's this class about? The study of life. All right, so what is water? It's made up of one oxygen atom and two hydrogen atoms. No joke, I have students flipping those around. H2O. It's not two oxygens, it's two H's, okay? So atoms are covalently bonded. So the bond that holds together the hydrogen to the oxygen is a covalent bond. They're sharing those electrons. Oxygen is highly electronegative, and that means that it pulls the electrons toward itself. So it shares them unequally. That makes it a polar molecule, but we'll talk about that in a little while. Electronegative. And of course we know its molecular formula is H2O, like I said before, and those are the covalent bonds. So in your notes, make sure that you are labeling those, okay? All right. Yeah, the notes are kind of short today, only 29 slides, so we should get through this pretty quickly. But we're actually doing it in two parts, because the second part has an 11-minute video that we're going to watch. So what does it mean to be polar? You know that the Earth has a North Pole and a South Pole, okay? You know that magnets have poles. They have a North and South Pole. And if you put the same poles together, they will repel each other, right? If you put unlike poles together, North and South, they'll stick together. You know that a human being can be bipolar. You've heard of that before. Maybe you know somebody who is bipolar. That means they have periods of depression and then periods of the opposite of depression, like extreme, So, and they vacillate, flip-flop back and forth between those two. So polarity means to have like two sides, okay? Yeah, you got it. So the molecule will have a charge to it. So for water, for example, has a positive charge on one side, where the hydrogens are, and because oxygen is negative, has a negative number, its side's going to be negative. So one side's positive, one side's negative. That's what polar means. That's what polar means. Why does this happen? It's because the electrons are shared unequally. We talked about that on the last slide. The oxygen atom pulls the electrons toward itself, making it more negative, and therefore making the hydrogens more positive. And the result is that water has amazing behaviors allowing life to survive and thrive on planet Earth. I call water the miracle molecule. Albert Einstein said it best. There's two ways to live your life. One is that nothing is a miracle, and the other is that everything is a miracle. So one way is kind of boring, the other way is more exciting. I like to think of everything as a miracle. So particularly water. Water is the only thing that does some of these amazing things. So how does it act? What are those things that water does to make us believe that it's a miracle molecule? Well, it acts like a magnet. There are, like we said, there are positive poles and a magnetic field around the water molecule. So those electrons are pulled towards the oxygen, making that negative and positive, okay? Now the hydrogen is going to have a positive charge, like I said, and oxygen negative, and then those similar poles will repel each other. So when water is sticky, right? And it sticks to other water molecules. And you're not going to get, if it wasn't polar, then they wouldn't stick to each other. And they'd bounce all over the place. Water would not form pools or puddles or lakes or oceans. It would probably be a gas and would be floating around the atmosphere. It does. There are water molecules in the atmosphere, especially in Florida. That's called humidity. But when it cools, it forms puddles and pools because it sticks to each other, because of this negative positive attractiveness with other ones of itself. And how it does that is through something called hydrogen bonding, okay? So here water molecules are coming together and forming hydrogen bonds between the positive hydrogens and the negative oxygens. So it's a weak bond, it's very weak. That's why you can easily pull water apart. When oppositely charged regions of different molecules, not the same, because the same they would repel, right? Likes repel, opposites attract, okay? So it's an electromagnetism. And so the attraction between the water molecules is represented by these dotted lines, and opposite charges attract, opposites attract, okay? And this visual does it for it. It just, makes it very clear. Okay, so now you're going to do a test yourself, but not in class. All right? Well, after the notes. Okay, so you have to go back to just like we did with the scientific method notes. You're going to go back into the notes and find the answers, and you can work with the people at your table to do that after this. Okay, if we have time to do it. Otherwise, it's homework. Don't give away the answers, Mr. Keene. Okay, what properties result from polarity? I love these pictures, they're amazing. This is just incredible. It's a swimmer who's coming up so fast out of the water, and the surface tension is allowing the water to stick in a form of the swimmer before it breaking the surface of the water. It's just a perfect capture with a camera that caught that picture. So when water molecules stick together, like I said, it's called cohesion. Co meaning the same in this case. So the same things sticking to each other. The opposite of that would be adhesion, and an easy way to remember that is adhesive tape, like Scotch tape or masking tape or duct tape, okay? Those are called adhesive tapes because they stick to other things, right? So adhesion, cohesion. Cohesion is sticking to itself. So the hydrogen bonds are all holding the molecules of water together to each other. Remember, what holds a single molecule together is covalent bonds. A lot of students mix up that covalent and hydrogen bonding. Hydrogen is weak. Hydrogen bonds are weak. Covalent bonds are strong. Okay? The result is that surface tension that allows a spider to walk on water, or an ant to be caught in a drop of water, or this to happen. You can actually take a tiny paper clip, the regular size paper clips, not the big ones, and you can float that on the surface of water. Or have you ever done the putting so many drops of water, you must have done this in physical science, on top of a penny to see how many you can bubble up on that penny before it spills over? All right, so the hydrogen bonds hold the water molecules together and resist stretching or breaking. So, and some animals can, like I said, stand, walk, or even run. So check this out. Well, not that one. This is something different. Okay. Is this supposed to play? No. I don't know. Oh, those. Yeah. Okay. So ignore these. That was just the answers to the last thing. And then this is in space. Water will stick to each other, the water molecules, and then form a ball in space. Okay. That's all that was. This is the video that I want to play for you right now. Right there, that's pretty cool. The water molecules have that tendency. Gravity takes over eventually, but they want to stick together. And so you saw them retain that form of that balloon when it was popped, okay? All right, and then basilisk lizards, also known as Jesus lizards, because they walk on water. They run so fast, they never break the surface tension. And we have these here in Florida now. Right here in Boca. I saw them at one of those wildlife parks we have just inland, or just on jog, actually, right up the road here. They're in there. The males have the crested heads. The females don't have a crested head. Anyway, they're invasive species. Someone's pet that got loose and they took over. And so they run so fast that they don't break the surface tension. It's pretty cool. That's how they escape predators. So what properties result from polarity? Okay, so one of them is capillary action. Now this is the movement of water against gravity. You've all seen it. You've held a tissue or something up to a spilled liquid. If you've ever gotten your blood tested, maybe for nowadays they do it all digitally and electronically. It's pretty amazing. But they used to, when you went to give blood, they would prick your finger with a little dot of blood, and they would take this little tube and they touch it to your blood, and the blood would go whoop, right up the tube. Okay, that's called capillary action. It's sticking. This is an adhesive property. This is adhesion now. So now we're not talking about water molecules sticking to each other. We're talking about water molecules sticking to other things. And so different surfaces. And so the water molecules will stick to the tiny tube or to the particles of paper towel, and they'll move up. They'll be pulled up into that. Okay? We know that that's called a graduated cylinder, and I've got some in the cabinet here. So graduated cylinder, if you use one of these, you know that you have that thing called a meniscus. It's a curvature in the graduated cylinder, and you always read the top of the meniscus, right, not the bottom. You read the bottom of the meniscus, not the top. Nice try, Mr. Keene. Anyway, and that's because water sticks to the sides and makes a curved pattern. And the rule is to always read the bottom of the meniscus when you're reading a graduated cylinder, okay? So remember, adhesion is sticking to different, cohesion is sticking together. And the smaller the tube, the higher the water will go. Now, trees work this way. Trees, we're going to learn more about plants, I think maybe next semester, but trees have vascular tissue, just like we have veins and arteries. They have something called xylem and phloem. Now, phloem flows down, and xylem goes up, okay? Xylem. X-Y-L-E-M. You thought it was Z, didn't you? Okay, and so those are tiny tubes in a plant that act like capillary tubes, and because of water's cohesive properties, it's easy for a plant to get water from the roots all the way up to the leaves at the top. Even those really tall sequoia trees out in the Pacific Northwest that are like 300 feet tall. So if the water is evaporating from the top, it has to be replaced from the roots. And so the xylem carries it up because of capillary action. So what other properties result from polarity? Okay, so we've got something called high specific heat. Now you may have learned about this in physical science. I taught 8th grade physical science before and high school physical science. So I know that I taught my students what specific heat is, but I don't know exactly what you or where you came from. So here's a list of some common specific heats of some materials that you are familiar with, like water and rocks. This is just basalt and granite or rocks. Maybe you have granite countertops at home. Iron is a metal. Copper and lead are also metals. And you can see water, liquid water, has the highest specific heat than any of these. As a matter of fact, it's got one of the highest specific heats. Let me explain it in a very simple terms, okay? Water resists temperature change. That's what high specific heat means. A low specific heat would be something that doesn't resist a temperature change. So, it's because the water molecules must be pulled apart due to hydrogen bonds. All right, so just pause for a second. Let me give you my scenario. So if I put water in a copper pot or an iron pot or aluminum pot, whatever, down here, and I turn the stove on and I wait for 1 minute and then I touch the pot, am I going to burn my finger? Yes, you're going to burn your finger. Why? Because metals have a low specific heat. They don't resist temperature change very well, right? But now, after that minute, I stick my finger in the water. Am I going to burn myself? No. It's only going to be maybe not even warm. Maybe warm, okay? Because water resists temperature change because it has a high specific heat. That's the easiest way to explain this concept, okay? Water can moderate or stabilize temperatures that way. That's why they use water to cool things like car engines and nuclear power plants. Okay, you've heard of water-cooled engines, right? You've heard of a nuclear meltdown? That's because the core somehow got separated from its water coolant. And so, human body, we remain stable because we are mostly water. We're big bags of water. Take the water out of us and we'd be a little pile of dust like this. That's all we'd be if you removed all the water. Marine environments remain stable. So the temperature change of the water in lakes and oceans, the larger bodies of water, don't change very much because of this high specific heat. And coastal climates, like ours in Palm Beach, have more mild climates. People move here because they like cooler summers and warmer winters. Go here to this county, which is only about an hour away, okay? Depending upon traffic, maybe 2. And it's going to be, at least in the summertime, if it's 85 here, it's going to be 92 or 95 there, guaranteed. And in the wintertime, if it's 65 here, it's going to be 55 there. It's going to be colder because the water regulates our temperatures on the shore. And that's why the beaches are the most popular places. The shoreline is the most popular place. So, and this is one of the reasons why. So, water absorbs energy during the day, right? Particularly during the summer, but yeah. And it cools the surrounding area. Because water can hold on to a lot of energy once it's heated up. It releases that heat at night and during cool weather. So, in the summer it's absorbing heat, and in the winter it's releasing heat, regulating those temperatures, warming the surrounding area. So it's only 5 miles from our school here in Spanish River Community High School on the corner of Jog and Yamato. Take Yamato all the way, maybe take some other side roads, don't have to go down, cross 95, go down here, and then go over the bridge, and then you're right at Spanish River Park, okay? And as the crow flies, it's only about 5 miles though. But in the heat of the day, we're going to feel a lot different. In the middle of the summer, when you went to the beach, it was cooler, definitely. But just go a short distance. It's amazing. Okay, so here's a question. This is in your notes. Warm land meets warm ocean, just like here in Florida. Which will cool faster when the sun goes down? Will the land cool faster, or will the water cool faster? Remember, water has a high specific heat, so it resists change. So yes, the land will cool faster, okay? All right, what other property results from polarity? Ice floating. Now, ice is less dense as a solid. Everything else that you can think of when it's a solid is more dense. So if I had this gold ring, my wedding ring, for example, okay? If I put this in liquid gold, would it float or sink? It's more dense than liquid gold, so it would sink. But water, when you turn water into a solid, you reduce the temperature and freeze it, like this frozen gold, it floats. It does the opposite. If you don't think that's a miracle, after everything I've said so far today, this is what makes life possible on Earth. Because if it didn't, when ice froze, it would sink. And then the entire lake and ocean would freeze from the bottom up, killing all life in the ocean. But instead, it freezes at the surface and floats, right? And it makes an insulating layer, protecting the life, like this beluga whale, under the water. That's why people can go ice fishing. They drill through the ice like a foot or two, when it's really cold. And the fish are still down there because they're protected by this layer of ice that floats on the top. It's just so amazing. Why is water the only thing that does that, And it has to do with this crystal lattice. The reason is that the molecules, when they start to freeze, they join together in this crystalline form that pushes the molecules apart more than if they were liquid, okay? Pushes them apart in this crystal lattice, and that makes it less dense. It makes the particles farther apart. Density means the particles are closer together, right? Less dense, the particles are farther apart. So if the particles are farther apart in that crystal 3D matrix called a crystal lattice, then they're going to float. Yes, there is a scientific reason behind it, but still, how did that become a thing to make life possible on this planet? Okay, I think the last one is the universal solvent. So, Universal means it's a good solvent. It doesn't dissolve everything. Like if I poured water onto this table, the table is not just going to melt, like some marshmallow or something like that, right? Or sugar or something, or a piece of bread. But it does dissolve a lot of things. It dissolves metals. It dissolves all kinds of things, rust and whatnot. A solution, and you should have learned a lot of these words in physical science, is made of a solute, right? The solute is what's dissolved, like salt in water or sugar in your tea. The solvent is the liquid. So in this case, the water, universal solvent. That's what does the dissolving. So salt, and then there's a solute and solvent water. Okay. An aqueous solution is a solution made with water. Aqua, from the Latin for water. Water-based solution, like this. Putting in salt, mixing it up, dissolves, makes a solution, okay? So what happens is the water surrounds the particles, like let's say it's a crystal of sugar, and it pulls the particle apart, allowing it to dissolve. And this is very important because it easily allows organisms to move molecules around their bodies. You eat a sandwich, goes down to your stomach. Now what? You can't take that sandwich and move it around inside your body and through your tiny vessels and into your tiny cells, microscope. It has to break those things down. And the only way to do that, your blood is mostly water and your cells are mostly water, is to dissolve those molecules in the water. And if water wasn't a good solvent, it couldn't do that, okay? So like dissolves like. Now because water is polar, it's going to dissolve polar molecules. It's also So there's hydrophilic molecules and there's hydrophobic molecules. Philic means loving, like the city of Philadelphia. That is Greek for loving of your brother. So Phila is loving and the Delphi is brotherly. So it's the nickname of Philadelphia is the city of brotherly love. Okay. There was also a Philadelphia in ancient times over in the Greek and Roman, empires. So philic means loving. So this is hydro means water, loving. And polar molecules, because water is polar. And ionic compounds are polar, like salt. Salt, ionic. Sodium chloride is ionic. Okay? And then hydrophobic. Phobic means fear, right? To have a phobia of something. It's actually this is all a lot easier than it looks at first, isn't it? And so water, fearing. So non-polar substances like oils and fats over here will not mix with water. Look, so that's your polar and non-polar. So sugar will dissolve, fats will not. Oil floats on water. Gasoline floats on water. You know that, right? So water is an amazing molecule allowing life to exist on our planet. If not polar in nature, life probably wouldn't exist. That blows my mind. Okay, so think about humans looking for life out in the universe. We just developed this new James Webb telescope and it's sending back these incredible pictures that are so much better than the Hubble Space Telescope. And our technology gets better, so we're going to be getting better at stuff like that. So what kind of evidence are we looking for? What do we generally look for first? If we're looking for life, we're going to be looking for that all important life-giving molecule, as far as we know, water. Okay? And Europa, this is just a little side thing. This is an artist's rendition of the surface of Europa, which is a moon of Jupiter. Okay? It's Jupiter's fourth largest moon, one of Jupiter's four largest moons. It's thought to have liquid water under its icy surface. Okay? It has all the elements thought to be key for the origin of life: water, energy, and organic chemicals. And And there are missions that are being sent to Europa that are going to drill through its cracked icy surface and search for life underneath. So we could have life somewhere that we haven't discovered yet in our solar system still. We just need to get there. That would change a lot of people's minds about science, you know. Oh, yeah, water, that was the answer there. Hopefully you wrote that down already. All right. So you're gonna do a test yourself, either right after this or for homework, okay? We're not gonna divulge these answers right here. 2 slides of it. Actually, this is the 3rd slide of it, part 2. Okay, so we're gonna stop here. So that's water, it's polar, and it's amazing. Here I just picked this. This is actually taken right here, you know where the breakers are in West Palm, okay? This is a whale shark. Somebody was diving out there over the reef, and a whale shark swam by with a whole bunch of the remora, those fish that use their modified dorsal fin to stick to a larger creature, sharks particularly, and follow them around for free ride, free food, whatever, okay? I just thought that was cool. So, we're gonna stop here. We do have something else to do, but if you do have some spare time in class, go back and do the tests yourselves. Otherwise, those tests yourselves are for homework.